Hello. Good morning. Good morning. Okay. The last subtopic we have done is the relationship between phase difference and path difference. So we spoke about what is phase difference and path difference separately, and the relationship between them as well. Then write down next subtopic. And we spoke about what is stationary waves as well. Okay, write down the next subtopic. Speed of a transverse wave. Speed of a transverse wave. Speed
So you're not sharing the screen.
Okay. Speed of the transverse in a string. Where the speed of a wave, transverse wave in a string, is given by square root of T over mu. Take it down, I'll explain you what does these terms mean. Okay, right. The speed of a wave, speed of a transverse wave, in a string is given by the above equation, in which T is the tension the string, and mu is the mass per unit length of the string. Where mu is the mass per unit length. T is the tension, mu is the mass per unit length. So that means one length of the string has what mass? Okay. Write down an example question. Quick question. Um, a transverse wave travel in a stream which has a tension (50 newtons) and mass per unit length of 0.5 kilograms per meter. Calculate the speed of the wave. Calculate the speed of the wave. Can you? A straightforward question. What's the answer? So guys, we can use V equals square root of T over mu. The tension in the string is 50 newtons. Mass per unit length is 0.5. So 50 over 0.5 square root. 50 over 0.5 is 100. So square root of 100 means it's 10 meters per second. That is the speed of the wave. Okay. Right. Then right. Guys, write down the next subtopic. Now we spoke about the generation of stationary wave. We spoke last week. When two waves of the same speed and frequency move in opposite directions and overlap, the stationary wave will be formed. Depending on the frequency, it can have different shapes. So I told it can have a shape like this or this or this, depending on the frequency. So now I'm going to talk a bit in detail about it. How depending on different frequencies, you will be getting different shapes. Okay. So write down the subtopic. Write down the subtopic. Different shapes of stationary waves. Different shapes of stationary waves. Okay. Now guys, let me see. Now listen to me carefully. There is a string. This has a length of, let me see, 5 meters. This has a length of 5 meters. And the speed we send a wave here, okay, in this direction. Let's say the speed of the wave is speed of the wave is 2 meters per second. The speed of the wave is 2 meters per second. We send a wave on this string at a speed of 2 meters per second from this corner to this corner. It will reflect here and it will travel in the opposite direction, and we continue to travel a string wave, original wave. So those two waves overlap and it can form a stationary wave. Now let me see at what frequency to form a stationary wave. What is the frequency we should use to oscillate the string to form a stationary wave? Listen to me very carefully. Listen to me carefully, okay? So guys, the first type of stationary wave that we call it as the fundamental wave. Fundamental wave. Fundamental stationary wave. Okay. Which is a shape like this. Which is a shape like this. So particles in this string will vibrate like this. Did I show you a video of stationary waves last week? Yes, right. So in fundamental mode of vibration, all particles will move like this. So here we see exactly half a lambda. One wave is this, no? So what we see here is exactly half a lambda. So that means for this to happen, lambda over 2 has to be 5 meters. So which means the lambda has to be 10 meters. Lambda has to be 10 meters. So by using V equals F lambda, now V is 2, no, I told you. Frequency at lambda is 10. So we need to start with a frequency of 0.2 hertz. So which means if you oscillate this string exactly at the frequency of 0.2 hertz, you will get a stationary wave like this. Yes. Can you remember the last week, the video I showed you? At certain frequencies, it was forming stationary waves. And when he was changing the frequency at certain frequencies, you didn't get a stationary wave. Do you remember that video? Can you remember? Not at every single frequency you will get a stationary wave. There are certain frequencies at which you get a stationary wave. He was adjusting the frequency, and at certain frequencies there was a clear stationary wave. Okay, so I'm telling you for this string, for this P, okay, which is 5 meters length string, and where this wave speed is speed of the wave in the string is 2 meters per second. If you exactly oscillate at 0.2 hertz, you will get this stationary wave. Understood? This is, we call the fundamental stationary wave, or we call it as the first harmonic. Fundamental stationary wave or the first harmonic. Okay. The next possible case that we can have is this one. The same string, we can have a stationary wave like this, with 2 loops. Here it was 1 loop, now with 2 loops. Still the length of the string that can't change, that will be 5 meters. Now you see exactly one wave is here, exactly one wave. So which means in this case, lambda is equal to 5 meters. Okay. Speed is still the same. The speed of the wave is not going to change. The speed of the wave is 2 meters per second. So now if you want to get this stationary wave, V equals F lambda. V is 2, frequency into lambda is 5. So frequency is 2 over 5. That means you need the frequency of 0.4 hertz. This we call as what? Second harmonic. This we call as the second harmonic. Okay. So if you oscillate at exactly 0.2 hertz, you will get this stationary wave. If you oscillate at exactly 0.4 hertz, you will get this stationary wave. And let me try the next possible case. Let's say this is our string which is having a length of 5 meters. We will get a stationary wave with 3 loops. 3 loops. So now how many lambdas are we seeing here? Here there is actually 1.5 lambda. This is one wave. This is another half a wave. So 1.5 lambda. So 1.5 lambda is equal to 5 meters. So the lambda is equal to 5 over 1.5 meters. So now I'll use V equals F lambda. V is once again 2 meters per second. Frequency is what I want to know. So lambda is 5 over 1.5. Cross multiply to get the F subjected. 2 into 1.5 is 3. 3 over 5, which is 0.6 hertz. So initial frequency was 0.2 hertz. The next frequency was 0.4 hertz. The next frequency is 0.6 hertz. Do you see a pattern? Do you see a pattern? People online, are you there? Can you hear me? Do you understand what are we doing here? So my question is, if you want to get the next pattern of fundamental next stationary wave, what is the frequency you need? 0.8 hertz, 0.2, 0.4, 0.6. If you want to get the next pattern of stationary wave, you need 0.8 hertz. That will be one with 4 loops. Okay, so this was second harmonic. This we call as a third harmonic. This we call as a third harmonic. So to get the fourth harmonic, you will need 0.8 hertz. So for the next one, it will be 1 hertz. The next one, it will be 1.2 hertz. Why does the wavelength change? Now see, speed is a constant. Speed is a constant. So when you are increasing the frequency, the wavelength will decrease, right? When you are increasing the frequency, obviously the wavelength will decrease, right? Because the frequency is the speed is anyway constant. Speed depends on T and N. T and the tension and the mass per unit length. So those two are not changing, means the speed doesn't anyway change. So while speed is remaining the same, if you are increasing the frequency, definitely the wavelength will decrease. Okay? Understood? Yes. So now I want you to copy this one. Wait, before that, we'll make a small note. Wait, don't write anything first. Wait. Right under that. Right under the subtopic, different shapes of stationary waves under that. Let's consider a string of length (5 meters) in which speed of the wave is 2 meters per second. full stop. There are certain frequencies at which stationary waves will be formed. There are certain frequencies at which stationary waves will be formed. Okay, take down this one, draw the pattern, and then label it the first harmonic or the fundamental stationary wave and find the frequency. This is a frequency. Done? Okay, then take down this one, second harmonic, that is with two loops. And the next one, third harmonic with three loops. Done? Done? Okay, this is the previous page. Okay. Right. Okay, then continue your note. So if the fundamental frequency is F naught, the fundamental frequency is F naught, then the second harmonic frequency will be 2F naught. Third harmonic will be 3F naught, and so on. So if the fundamental frequency is F naught, then the second harmonic frequency will be 2F naught, third harmonic will be 3F naught, fourth harmonic will be 4F naught, and so on. Okay? Any questions? Any questions, anyone? Right, fine. Okay, guys, we'll do a couple of questions from the textbook. I'll pick these two questions. If you don't have the question, write down. This first question says, a guitar string of length 75 centimeters. A guitar string of length 75 centimeters vibrates in its second harmonic. The speed of waves in the string is 420 meters per second. What are the wavelength and frequency of the standing wave? Standing wave means another word for stationary wave. A guitar string of length 75 centimeters vibrates in its second harmonic. The speed of the waves in this string is 420 meters per second. What are the wavelength and the frequency of this standing wave? So guys, second harmonic means it's going to be a stationary wave with two loops. It will be a stationary wave with two loops. Okay, and then the length of this string is told to be 75 centimeters. And the speed is given 420 meters per second. So question is to find the wavelength and frequency. There's nothing to find in the wavelength. Definitely the wavelength is 75 centimeters. Because 2 loops means exactly this is one wave, right? So the wavelength is going to be that, which is 75 centimeters. Or in meters, you can give it 0.75 meters. Then to find the frequency, we have to use V equals F lambda. V is given 420 meters per second. Frequency into the lambda is 75 centimeters. We need to put it in meters, which is 0.75. So the frequency is going to be 420 divided by 0.75, which is 560 hertz. 560 hertz. If you have any question, you can ask. Any questions? Atik, Ahmed, any questions? Hello. Amna, Araniga, Ashmita, Bilal, Tinura, any questions? Humera, Rima, Sadurshan, Talha, Zaki. Okay, so the wavelength is 75 centimeters and the frequency is 560 hertz. Right, the next question. Second question says, how fast do waves travel? The second question has 2 parts, A and B. How fast do waves travel in a string that is held under 90 newtons tension and has a mass per unit length of 4.8 into 10 to the power minus 4 kilograms per meter? How fast do waves travel in a string that is held under 90 Newton tension and has a mass per unit length of 4.8 into 10 to the power minus 4 kilograms per meter? Okay, then so for that we anyway use V equals T over mu square root of the entire thing, right? So the tension is 90. The mu is mass per unit length is 4.8 into 10 to the power minus 4. And then you need to get the square root of the entire thing. How much is that? Is it 433? Meters per second? Yes, 433.01, so 433. And the next part of the question says, if the string is 74 centimeters long, calculate the fundamental frequency. Fundamental frequency is 74 centimeters long. So guys, the fundamental frequency means this mode of vibration, right? This is the shape of the stationary wave, just one loop. One loop, and the length of the string is 74 centimeters. So now you should understand that this is half of the wave, right? This is half of a wave. Full wave will be like this, and this is half of a wave. So lambda over 2 is equal to 74 centimeters. So lambda is equal to cross multiply 74 into 2 is 148 centimeters. That is 1.418 meters. That is the wavelength. So they're asking for the what? fundamental frequency. Use V equals F lambda. V is 433. Frequency, fundamental frequency is what we want. Lambda is 1.48. So the frequency is going to be 433 divided by 1.48. 433 divided by 1.48, which is 292.56. So I'll take it as 292.6. That's the fundamental. Is that okay? Any questions? Any questions? Done? Right. Okay. So that's about different types of stationary waves. Okay. Guys, write down the subtopic. Intensity of radiation. Intensity of radiation. Intensity of radiation. Okay. What is power? What is power? Energy passing through a point in a unit time. No? Energy passing in a unit time is power of a wave. So what is intensity is? Isn't it? Okay. There's a intensity means how much power falling on a unit area. Now let's say there is some waves, radiation falling on a surface. Let's say this surface has an area of A. And let's say some radiation is falling on it. Okay. Some waves are falling on it, passing through it. Let's say it has a power P. Then what is meant by the intensity? Intensity is power passing through a unit area, which means power over area. Okay. Intensity is equal to power over area. What is the unit of power? Unit of power is watts. Area is square meters. So the unit of intensity will be watts per square meter. Okay, take it down. Intensity is power over area. power passing through a unit area. Right under that. Intensity is the amount of power passing through a unit area. Okay, is the amount of is the amount of power passing through a unit area. Right on the question. A wave with a power 200 watts incidence on a surface with an area (4 square meters). Calculate the intensity of the wave so that's very straightforward. Intensity is power over area, that is 200 over 4, which is 50 watts per square meter. Watts per square meter. Right to the next question. A radiation with intensity 500 watts per square meter passes through an area of 7.5 square meters. Calculate the power passing through the area. A radiation with intensity 500 watts per square meter passes through an area of 7.5 square meters. Calculate the power passing through the area. So guys, intensity is equal to power over area. If you cross multiply, power is equal to intensity into area. So what is intensity? 500. What is area? 7.5. So 500 into 7.5 will be 3,750 watts. That's the power. Okay. So that's about intensity. Okay. Okay, guys, write down the next subtopic. Refraction of light. Refraction.
Can you go to the previous page for a second?
Is the previous page.
Okay, sir. Thank you.
Refraction of light. From your O levels, you know what is refraction, right? What is refraction? What is refraction? Yeah. Guys, what is refraction? Can you tell me what is refraction? Yes. When light is moving from one medium to another medium, it bends either towards the normal or away from the normal. Yes. That is we call as a refraction. Now let's say this is the boundary between two medium. Let's say this is glass. This is a glass block. Okay. And this is air. Now when the light travels from, so this is the light falling at this point. We draw a normal here. The line which we draw perpendicular to this surface, we call it as a normal. So when the light is traveling here from air to glass, so air is a less dense medium. Glass is optically a denser medium. So when the light is moving from less dense medium to denser medium, it will bend towards the normal. It will bend towards the normal. Correct? It will bend towards the normal. Or let me take another example. Now the light is traveling from this glass to air. So we have a glass medium. Now the light travels from glass to air. It's trying to move from glass to air. So in that case, it is moving from denser medium to less denser medium. It bends away from the normal. From the normal line, this is the dotted line I'm showing, the perpendicular line is the normal. So when it is moving from denser to less denser medium, it bends away from the normal. Okay, so this we call as what? Refraction. You have done this once. So when the light entering from denser medium to less denser medium, it bends away from the normal. Moving from less denser medium to denser medium, it bends towards the normal. Correct? Right. So right under that, wait, don't draw it. Wait. Right under that. When light travels from one medium to another, when light travels from one medium to another, it deviates from the original path. This is known as refraction. Okay. And then right below that, when the light travels from optically denser medium to less denser medium, when the light travels from optically dense medium to less denser medium, it bends away from the normal. When the light travels from optically denser medium to less denser medium, it bends away from the normal. And vice versa. When the light travels from optically denser medium to less denser medium, it bends away from the normal. And vice versa means when it is traveling from less denser medium to denser medium, it bends towards the normal. So draw this diagram first. It's trying to travel from glass to air, it's bending away from the normal. The next one, traveling from air to glass, it's bending towards the normal. Draw these two diagrams. That right now, guys, here from your O levels, once again, you know the angle this light makes with the normal. This is the incident angle. Sorry, this is the incident ray, right? This is incident ray. This is the refracted ray. Correct? So the angle this incident ray makes with the normal, we call it as the angle of incidence. Angle of incidence. So this angle it makes with the refracted ray makes with the normal, we call it as the angle of refraction. Okay. The angle the incident ray makes with the normal, we call it as the angle of incidence. The angle the refracted ray makes with the normal, we call it as the angle of refraction. Okay. But on a general note, forget about this air and glass and story video. I will call this the medium 1. I will call this the medium 2. It can be any medium, glass or water or perspex or air or any plastic or whatever, polythene or whatever medium. I'll call it 1 and 2. So the angle here I will take it as theta 1. Here the angle I will take it as theta 1. Here the angle I'll take it as theta 2. Then there is a relationship between these. What is that? This is the relationship given n1 into sine theta 1 equals n2 into sine theta 2. n1 N1 into sine theta 1 equals into sine theta 2. What is N? What is N? N is the refractive index of the medium. Depending on its optical density, there is a value given for that medium, which we call as the refractive index. N is the refractive index. So N1 means the refractive index of first medium. N2 means the refractive index of the second medium. Okay. Right. Wait. Now let me right below this. There is a relationship between the degree of refraction and the refractive index of the media involved. There is a relationship between the degree of refraction and the refractive index of the media involved. So guys, let me take a general boundary. Okay. I will just take I'm not specifying what is what medium. Let's say it refracts and it goes like this. I will take this angle to be theta 1, this angle to be theta 2. This is medium 1. This is medium 2. Take it down. And the refractive index of this medium 1 is N1. Refractive index of medium 2 is N2. Done? So the relationship is we can write N1 into sine theta 1. N1 sine theta 1 equals N2 sine theta 2. Okay. So what is N1? Refractive index of medium 1. Into refractive index of medium 2. Okay, then guys, I'll take can you check and tell me what is the refractive index of air? Can you Google and check what is the refractive index of air? Google and check refractive index of air, which is 1.000293. Google says 1.000293. Can you all check? But we usually take the refractive index of air to be 1. Since it is 1.000293, it's taken as 1. Okay. Write down a question. A ray of light enters a block of glass which has a refractive index 1.5. A ray of light enters a block of glass which has a refractive index 1.52 as shown in the diagram below. Calculate its angle of refraction in glass. So this is the block of glass, and let's say it incidence like this. The angle of incidence is, I'll take it to be 40 degrees. The angle of refraction is what needed. Give a try. Okay, so we'll use the equation n1 sine theta 1 equals n2 sine theta 2. So n1 is, I will take the first medium is air, n1 is 1. Sine theta 1 means sine 40. N2 is the second medium, which is glass, 1.52. Sine theta 2 is the sine R we have to find. So use your calculator to find the sine R and then get the sine inverse, you get the R, which is sine 40 divided by 1.52. That is the sine R, and get the sine inverse of that value. That gives you how much? $25.0, 25 degrees. Are you getting 25 degrees, people? Are you? Yes. Any questions? Right. Let's write on the next subtopic. Critical angle. This is again something that you have done for your O-levels. So guys, critical angle is now, let's see, we have a medium here. This is denser medium. let's say this is less denser medium. Let's say the ray is moving from denser medium to less denser medium. When it is moving from denser medium to less denser medium, it bends away from the normal. So the ray which comes here, let's say it bends like this. Now, when you increase the angle of incidence, let's say you make it for this angle of incidence, it bends away like this. And then when you increase the angle of incidence, let's say for this angle of incidence, it bends away like this. Okay, you increase the angle of incidence, the angle of refraction will also increase. Now let's say when you further increase the angle of incidence for an angle of incidence like this, the angle of refraction becomes exactly 90. Exactly 90. Okay. Then this angle of incidence at that instant is what we call as a critical angle. Critical angle. Understood? So when the light is entering from denser medium to less denser medium, the angle of incidence which makes the angle of refraction to be 90 degrees is what we call as a critical angle. Okay. Understood? Right. Okay. Now wait. First, don't draw right under that. When the light is traveling from denser medium to less denser medium, it bends away from the normal. When the light is traveling from denser medium to less denser medium, it bends away from the normal. Full stop. For a particular angle of incidence, the angle of refraction is 90 degrees. For a particular angle of incidence, the angle of refraction is 90 degrees. Full stop. That angle of incidence known as the critical angle. That angle of incidence is known as the critical angle. So let's draw this diagram. Draw this diagram. Okay. Right now, see guys. Now we already have an equation for this, so I'm going to use that equation. Now N1 sine theta 1 is equal to N2 sine theta 2. Now let's say this is denser medium is any medium. It can be water or glass or anything. And let me take this less denser medium to be air. Less denser medium, if I take it as air, so then it's going to be N, the denser medium's refractive index, I will take it as N. Sine theta 1 is sine C. N2, the refractive index of the less dense medium, N2 is 1 if I take it to be air. Sine theta 2 is sine 90. Okay, if it is air, N is 1. Theta 2 is the angle of refraction, which is 90 degrees here, clearly 90 degrees. So then what is happening? N into sine C. 1 into sine 90. Sine 90 is also 1, which is 1. 1 into 1. So sine C is equal to 1 over N. We have made this equation even at O levels. Critical angle C is given by 1 over N. Understood? But this is a critical angle when the outer medium is air. If the outer medium is something else, then it will be different. Then you have to use this equation and figure it out. Okay. So guys, in your diagram where you have written less dense medium, within brackets make it air and take down this one. Just take it down and you can take a break. I'll be back in 15 minutes. We'll come back and continue. Welcome back, people. Hello, are you there? Can you hear me? Can you hear me? Yes. Right. Okay, guys, we'll do a couple of questions from the tute, from the textbook. No, we'll write down the subtopic. Write down the subtopic. Total internal reflection. Total internal reflection. Total internal reflection. So guys, we spoke about now if there is a denser medium and if the light is traveling from denser medium to less denser medium, when the light is traveling from denser medium to less denser medium, it bends away from the normal. It bends away from the normal. So when you increase the angle of incidence at one particular angle of incidence, the angle of refraction will become 90 and it will go through this boundary between the two medium. And if you increase the angle of incidence further, then what will happen? It will reflect back into the same medium. If you further increase the angle of incidence, it will reflect back into the original medium. What do you call that? Total internal reflection. Okay. So once again, guys, this also happens when the light is traveling from denser medium to less denser medium. It will not happen from less denser medium to denser medium. So what is happening when the angle of incidence is more than the critical angle? The light will reflect back into the original medium, and this is known as total internal reflection. Right under that. When the light is traveling from denser to less denser medium. When the light is traveling from denser to less denser medium, and when the angle of incidence is greater than the critical angle, and when the angle of incidence is greater than the critical angle, the light will reflect back to the denser medium. The light will reflect back to the denser medium. This is known as total internal reflection. So in that case, guys, the angle of incidence will be equal to the angle of reflection. This is denser medium. This is less denser medium. Check it out. Okay, guys, that take that past paper from Unit 2, May 2020. May 2020. We have done the first couple of questions. Turn to section B, question 11. Section B, question 11. Section B, question 11. A block of glass is submerged in a container of water. A ray of light traveling in the water is directed towards the glass surface as shown. So there is a glass inside water. Refractive index of water is given 1.33. Refractive index of glass is given 1.52. Calculate the angle of refraction within the glass block when theta is 43 degrees. Calculate the angle of refraction within the glass block when theta is 43. Okay, now let me extend this normal here. So now comparing to, if you compare glass and water, water has a refractive index of 1.33, glass has a refractive index of 1.52. The one who has a higher refractive index will be the denser medium. So basically here what's happening is it's traveling from water to glass, means it's moving from less denser to denser medium. Okay, so less denser to denser medium means it will be bending towards the normal. So I would expect a path like this. Calculate the angle of refraction, I will take it as R. So using the equation, sine theta 1 into n1 is equal to n2 into sine theta 2. That's the equation. So the refractive index of water is 1.33 into the angle is sine 43. Then into the refractive index of glass is 1.52. Sine theta 2 is what we have to find as the angle of refraction, which is R. Okay. Can you solve this equation and please tell me what is the value of R? Please tell me the value. How much is that? Yes, yes, yes. 36.6 is correct. That is the angle of refraction inside the glass block. Okay. Then the next part of the question, determine the critical angle for light at a glass water boundary. Now talking about glass water boundary, what is the critical angle? There's now listen. Now let's say the light is entering from glass to water. This is the normal. It's entering from glass here to water. This is 90 degrees. So this is what we call as a critical angle. So now using the same equation, n1 sine theta 1 is equal to n2 sine theta 2. So n1 for glass, if I take the refractive index 1.52, sine theta 1 is a sine C we have to find. N2, the refractive index of water, which is 1.33. Sine theta 2, the theta is now 90 inside water. So solve this equation and find the C and then get the sine C and get the C. That's going to be the answer, which is 1.33 into sine 90 divided by 1.52. That is the sine C. And get the sine inverse of that. That's going to be the C, which is 61.0 degrees. Are you getting 61.0? That is the critical angle for glass water boundary. Understood? So you can't just take it as sine C equals 1 over n. Sine C equals 1 over n you can take if it was glass air boundary. So since it is not glass air, since it is glass water, this is the equation you need to use. Always this equation will work. N1 sine theta 1 equals n2 sine theta 2. Is that okay? Any questions? People online, any questions? Any questions? Yes. So sine C equals 1 over n you can use if it is glass air or water air. If the air is the less dense medium, then you can use sine C equals 1 over n. That's okay. But in these cases, you can't use. Right? So that was question 11. Okay, guys, try question number 17 for homework. 17th one, try it for homework. Okay. Any questions? Any questions? Okay, then that's it for the day. Have a nice weekend. See you next week. Bye. Take care. And guys, we will be having a couple of cover-up classes. I think I have already informed you. Well, towards the end of the month, we will not be having classes. The last 2 classes, we will be having 2 cover-up classes for that. So next Saturday, anyway, we have the class. So there will be 2 more cover-up classes. I'll let you know about it when are we having it. Okay. Bye. See you. Take care.